Okay, thank you, everyone. So this is a work that I did in conjunction with my supervisor at the University of Singapore, but also I got great support from Chris and Samuel, who are the maintainers of the library, and I very much appreciate the support. So my main motivation for this work was that I was working with modeling social interactions. How people the likelihood that people come about with each other, like say in a conference like this, and then you can imagine social interactions like this plot on the left. Like so these dots are when people show up in your sensor, and then like the likelihood that you're gonna show up depends on previous information and your previous history, and this is and then it also depends on who are you connected with. So if you're connected with certain people, you're more likely to show up at a certain time, let's say. And you can describe this, let's say, intensity, this latent intensity, with a graph like this one on the right. So when I was looking for a library to model this kind of interactions, I couldn't find a general purpose library where I could just define the intensity function, and then it would simply simulate the data that I was interested. So then I came across with differential equations.jl, and then I noticed that they were trying to simulate something very similar. So there were the JumpProcesses.jl, which at the time had a different name. It was called diff_jump. And then I see there was a lot of similarity, because the differential equation can be decomposed in three parts. So there will be a deterministic component, so the dt part, and then there might be two stochastic components. So the first one, it's maybe more familiar to most people, is the diffusion component. So for any time interval as small as you want, there's always going to be a change. You don't know which direction you're going to go, if up and down, but there will be a change. So what changes with the jump component is that for a long period of time, there will be no change. There's only there's a latent intensity, but the system will undergo a sudden change at a specific period of time. So it's a discrete change, and then to model this type of change, you need different types of algorithms than the ones you use for the deterministic and for the diffusion component. And at the time that I started contributing to the library, there was no method to simulate jumps that with any type of variable intensity rate. There was one method, but it was not very efficient. And then my objective was to make it more efficient and fast for any type of intensity. So jump processes or point processes can be used in a variety of applications. So here I listed a non-comprehensive set of examples. So they are used in seismology, where the algorithms that I improved came from. Also neuroscience. I think you just saw in the presentation that came about. In finance and biochemistry, and the field that I'm interested in social media and social interactions. And I can summarize point processes by that figure. So you have that wave that is most time it's continuous, and it's called intensity, and then you have the actual dots that are the actual events. And here I want to make a digression and say why point processes and jump processes are the same. Is the view that point processes are usually you can think about as a ruler, but you don't know where are the numbers in the ruler. So basically what you're saying is that, let's say from time 1 to time 2, you have 5 points. So your ruler will have a quantity equals to 5, and then usually when you're dealing with jump processes, you may be counting since the beginning of time. So you don't necessarily need to have the concept of measure, and you don't need to maybe overcomplicate. But the key idea is that there will be only one event at a certain period of time. The assumption is that you cannot have multiple events happening exactly at the same time, but you can assume that there is a mark So if an event happen, you can draw from a distribution, and that distribution can tell you many things about what happened at that exact time. And then if you're dealing with point process on the real line, so the support is time, you can actually describe any point processes with a conditional intensity. And the conditional intensity it basically says what's the rate of the process per unit of time. So how many events you expect that will happen within the next second. And then it can be, and then you take into account, the whole history of the previous event. So in a sense, there is some cases where the jump might be a Markov process in the sense that you only use the information from the previous step. But then in a more general sense, your process can depend on your infinite history since the beginning of immemorial time. And then another interesting thing is then once you define the conditional intensity, you can actually transform your process to using the sum of the conditional intensity since the beginning of time to something called a compensator. So the compensator is a way to transform your temporal point process or your jump process into a homogeneous point process with unit rate. And under the hood, what most simulators that simulate this type of data do is try to go from your Poisson distribution then to your complex and difficult model by using a transformation that might look like that, and also by using different techniques that try to create a mapping between the exponential distribution and your crazy model. So the contribution then of the new additions to the library were to develop a method that would allow me to have any type of conditional intensity that I wanted, and then I would provide. Then you provide to the library the rate, and then in return you're gonna get the points that will be simulated, and that was the main objective. And then there are three techniques for simulating a jump process. So the first one, which is the most intuitive that I touched upon before, is the inverse method. So you take your conditional intensity, then you invert into the Poisson distribution, which has interarrival time in terms of an exponential distribution, and then you just solve that system. You just solve this system here over and over and over again. But the problem is that with this approach, it's not very efficient because you have to evolve the conditional intensity at the same time that you need to find the time for the next event, and that can be very expensive because you're trying to nail that exact time where the system is where one side of the equation is gonna be equal to the other. The other approach is thinning. So you construct a process that is a homogeneous process, and then you thin that process. So it's like you have water going through a sieve, and then you try just to let some of the water through, and with that, then you can reconstruct your process. And finally, when you have many processes happening at the same time, you can use some sort of queue to queue like the next few events, and then as you update the queue, you generate new events. So these are the three main approaches that you can take to this problem. And here is a very simple example of how you would do with the library. So in this case, you just want to simulate a process where a point happens every 4 units of time. It's very simple. But here's just to illustrate how you do it with jump process. So first you define the rate. So this would be the rate, and then the effect is like what happens when that point takes place. So in this case, we just adding 1 to our variable u, to accumulator, and then with the rate and with the effect we construct the jump. In this case, a constant rate jump, and then we define the parameters of the model. we define the type of problem we are solving. So in this case, a discrete problem, because we don't need to evolve time in continuous steps. And then with that, we create the jump problem. And eventually we solve using the stepper that's provided by the jump process library. And I'll go in more detail after, but here I inverted a little bit the order of events, and then I'd like to maybe first talk about the benchmarks, so you have an idea of like how fast the library is and how it compares with other contenders. So for that, we contributed with 2 new benchmarks. So one of the benchmarks is a multivariate Hawkins process, and another is a synapse model. So the first one that I mentioned is the Hawkins process. So you can think of it as a mutually exciting process. So your conditional intensity has a base level, and then you have that every time that an event happens, that either your event or an event that you're connected with, so that can influence your own event, that will increase the intensity by a rate alpha, and at the same time, like that intensity will decrease with an exponential rate modulated by the term beta. So the further you go from the time that an event happened, like that influence is going to go away. Like you can implement this rate like it is in Julia, or you can implement a recursive approach, because in this case this also turns out to be a Markov model, because we can just look at the previous time and then keep changing this parameter phi, and then you see that that in this particular case, it makes a big difference for the simulation. So, but here I just want to illustrate that with the current implementation, you can implement any type, any of these 2 types, and it would work just fine with the library. But of course, with significant performance differences. And then here, that's how you do with Julia. You define the rate, then you define the effect, and then as we'll see later. For the approach that I'm introduced, the Coevolve, you also need to define the upper bound of the process, and then the interval for which it's valid. But we go into more detail after. And so in this case, this is how like maybe processes are connected with each other. So you have a graph, and then here you have the orange, the blue, and the green. These are displayed in panels A and B. And then here it just demonstrates it's a quantile plot to demonstrate that we're simulating correctly. So ideally they should be aligned with the exponential distribution, as in this case. So you can see that when someone said that this is spikes of like when event happens and then they fade exponentially. And here I compare then with the different approaches. So before, the library could only solve this type of problem with the direct approach. And then you see that, so here is a network with 10 nodes, but here I simulated for 100 until 100 nodes. And then before, we could only simulate up to maybe 20 nodes. Then after that, the library couldn't finish the simulation within the time that I allowed for the benchmarks. And then the same took place maybe if I use another library called PDMP. If I just use the brute force approach, it also not finish. And then as I implemented the Coevolve approach, you can see that it significantly improved the performance. So if you use the brute force approach, which you get that it completes on time, but it's a bit slow. But then if you use a recursive implementation, then it's one of the fastest approaches. And then as it reaches a bigger and bigger network, it starts to lose a little bit from the PDMP approach using the derivative of the model. And then this is because the approach that as we'll see later uses the thinning process very aggressively. But in any case, it's very competitive, and then nice thing is very flexible. Now I also implemented another benchmark that this was a response from a discourse thread. So Roman Velds, he asked like, oh, can somebody try to how to run this model that I'm publishing like and get better results? So I accepted the challenge, but unfortunately I didn't I didn't manage to beat them. But I generated many insights because like it was quite straightforward to implement. Like there was a lot of like remapping of variable of one type of implementation to another, but then what I found out is that like with the approach with my approach, you end up like doing a lot of rejections as you think the process, but you still can be quite competitive. And then as you develop better, as in the future, maybe we develop better rejection approach, so you can potentially even match the performance of the other model. And then here is these are benchmarks that were read in the library, and it just shows that the Coevolve approach, which is the last one, remains competitive with the other ones. And then in this case, the jumps are constant. So then of course like Coevolve is designed for variable rates. So it's not as fast, and probably like needs some investigation, but it's still quite competitive. So very general. So here I'm gonna delve into how it all works a little bit, and how jump process and differential equations are connected with each other. And then so basically jump process is like it's a fancy callback for that is provided. So differential equations allow you to provide callbacks, and what jump process does is it's a fancy callbacks for point process. So basically, what a discrete callback needs is a condition and effect, and that's exactly what we provide in the what jump process provides in the library. So basically, we overload the callback, the aggregators. That's what here in the table you see like this. There's many different types of aggregators. So we overload this to have it be a rate and effect at the same time, and also initializer. So when you provide an aggregator, you basically like we basically like taking this the aggregator, that the name that you gave, and then calling initializing the structure for the callback. And then here usually we have the condition. So the condition so the condition for the callback is usually like before we reach that time, we just telling the stepper, okay, you're gonna have to step at that exact time. And then the most important part is actually the effect, because we know because once we stop at that time, we actually have to predict. We actually have to tell the stepper when they're gonna have to step next. So we're gonna say, okay, before you move on, I'm gonna do some computation here, and then I'm gonna tell you when's the next time you're gonna have to stop, and that's what the effect here is doing. But sometimes we don't need to actually to use like continuous steppers, because sometimes we're just interested in evolving like a jump only process. So the library also provides its own steppers. So the way differential equation usually works is that you give a stepper, and then it tells the differential equations JL like how it should step, like so from time T1 to T2, like how big is the step and all of that. But with jump process, if you just want to do jumps, like you don't need to have like such a fine-grained stepper. Like you can just step to the next jump, and the way it does that is by providing a custom stepper, which is called the SSA stepper, and then basically it goes and just steps from jump to jump to jump without having to do like all these small changes. So it can be very useful, like if you're just doing, modeling like jumps. And then of course, because this is integrated into the differential equations library, jumps can also provide a way to step with continuous integrators. So this is what I'm illustrating here. So the aggregator types. So we have 3 types of aggregators, as I mentioned before. So for the case of the inverse method, like there are no aggregators available because it requires the continuous stepper. But for the other types, the thinning and the queuing, it can use the SSA stepper that we provide, and then basically what you have to tell JumpProcesses.jl is okay, which aggregator I'm gonna use, and then what type of jumps I'm gonna give you, and then additionally some aggregators like Coevolve also require a dependency graph. So there are 2 types of jumps. So either you have a constant rate jump. So this only requires that you provide the rates and then the effect. So the effect here is not the same effect as in the callback effects that you might see in the differential equations.jl library, but it's an effect like what happens to that, what happens to your model when the jump happens. So in terms of the constant rate jump, and then also like for the variable rate jump, in addition to the rate and the effect, you also have to provide if you want to use the new aggregator, the Coevolve aggregator, you need to provide the upper bound. You need to provide the upper bound. So I will show you later what I mean by that. So an upper bound for how long, for upper bound for the rate. So you have to guarantee that the rate's not going to be higher than your upper bound throughout the interval that you also have to provide. So the rate interval. So let's say your rate interval is a function that says, okay, until time 10, my rate is not going to be higher than 100. But this can also all be, these are functions that you have to provide to the aggregator. And then L rate is a helper, so you can provide that, but you can also choose not to provide. So if you know that your jump will always have a base level rate, so it's a good idea to provide, because that will ensure that that when you're thinning, as I will show an illustration later, that you can reject it faster. Okay, so here's where I explain thinning. So basically, what happens is, like, let's say you have so let's say you started at time 0, and then you have this process, and then you had 2 points that took place, and then now you're at time t. So you have like many processes happening at the same time. So one of the processes is the dotted line here, and then as you add all the intensities together, you end up with the full line. And basically, what thinning does is that, like, we define a process that is this square box here, and then we sample from that square box. That square box is a process with constant rate, and then we sample from that box, and then we get a candidate point, so the gray one here, and then we have to decide, oh, should we accept or should we reject it? And then to do that, what we do is we sample from the uniform distribution, and then using the boundary as the maximum of the uniform distribution. And then if it falls below your rate at that point in time, so at this point where the candidate is being evaluated, then we're gonna accept. And then if it is above, then we reject. And then if your candidate is after L, so the time of the interval, then we reject it automatically, and then we move on. So this is how thinning works. So before that, JumpProcesses.jl used to only handle constant rates efficiently, and there's a lot of tricks you can use. So here I illustrate some of the tricks that they're using here to make the process more efficient. And then if you're using one type and another, it's using different tricks. And then with the Coevolve, like I took a step back, and then I went back to the thinning algorithm. And then my main idea was well, to queue everything. Like, so you usually you define processes that are connected, but they are not like densely connected. They're just sparsely connected with each other. And then the key difference is that now we can think together with the ODE. So if you want to incorporate the jump process with an ODE, now we're stepping at the same together with the model, and then it becomes more efficient and more compatible. So that's it. Thank you very much for coming. Here are some suggestions for way forward. So if anybody wants to contribute to the library, maybe you want somewhere to start, here are some suggestions. And I hope that you use the library and leave comments, issues if you have any problem. Happy to address. Thank you.
Do we have any questions from the audience?
A lot of the distributions, I'm over here, it's hard to tell, are in distributions.jl, defines a lot of distributions. And separate from the distributions, it has samplers that you can sort of use specialized samplers that do rejection methods. Were any of those useful in this? Is that architecture useful for writing something like this?
Yeah, so distribution.jl, I think like it's useful for like sampling from distributions, but when you have a process, so it's like you want to sample a random function, like so in that case, like in the case of point process, you want to sample a random measure. So then it's a bit more difficult than to describe that the function you want to sample, because the space of like measures in this case of a point process is too big. It's like you cannot describe it like, I guess, algorithmically. Maybe you could, I don't know. But then you have to then then it was not possible. Like the short answer, maybe it's possible if you have wrappers, and then that's where then I came to this approach to use JumpProcesses.jl.
So I just wanted to say thank you, because I use jump processes in my research, and I ran into like exactly this problem of like I wanted to handle time-dependent rates, and I saw like your method was merged in like 1 month prior, so it's like a great feeling. You can just switch it out. So.
That's great. That's a great feeling for me as well.
Okay.